Hello, Math 30-2 and welcome back. Today we are doing probability lesson 6 where we're looking at permutations and combinations. So if you remember from earlier classes, we looked at certain things where we were drawing cards and we're just looking at how many situations or how many hands we could have with 2 kings and an ace or something like that. Now we're going to look at those and bring it a bit farther. We're going to the probability of getting a hand with 2 kings and an ace, which is a lot more practical and a lot more used in real life. Okay, so just for a little review, we have factorial notation, so we have to remember what factorials were. We have permutations, and if you remember, permutations mean order matters. We also have permutations with repetitions, where you divide by the amount repeating on the bottom, right? So if you had 3 4s, well, you divide by 3 factorial, and then 2 2s, you have 2 factorial. Okay? Now, the other one is combinations. Combinations, order doesn't really matter for that one. So here is our very first example. It says, 2 cards are selected without replacement from a deck of 52 playing cards. Determine the probability that both cards are kings. Okay, so first we're looking at both cards are kings. Let's look at the multiplication law. Multiplication law means, if we're looking at this, well, there's 4 out of 52 kings in a deck of cards, right? So if we pick the first one, you have a 4 in 52 chance, which is the same as 1 in 13. And then we have a 3 in 52 chance that the 3 in 51 chance that the second card is a king. Okay, so 4 in 52 the first one, 3 in 51 the second time, which gives me a total of 1 over 221. All right? Now, that's kind of the long way. For this one, it is very easy because we're only looking at 2 cards. But if we're looking at a bunch of cards, it's easier to choose the combinations method. And the combinations method, you're just going to use your calculator to do anyway. So here we go. Out of how many kings do we want? Our hand, we want 2 kings. And there's a possibility of 4, but we only want 2 kings. So out of 4, we want 2 kings. Now, how many cards are there in the deck? In a deck, there are 52 cards. And all those 52, we're choosing 2. So this is my total possibilities. This is the wanted. And if we plug that into our calculator, we'll get the same thing, 1 over 221. Okay? Now, let's look at example number 2. In a card game, you're dealt 5 cards from a pack of 52 shuffled cards. When you look at your cards, what is the probability expressed in combination form? So we're looking at in this form here, combinations. So we're looking at it in this form here with combinations. Okay? So if we look at this, it says, example 2, we're getting 5 cards, and it's combination. So what is the probability of 4 aces? So, well, if we're looking at only 4 aces, I'll just readjust this so we can get to our sheet better. So if we're looking at only 4 aces, well, out of 4 aces, we're choosing 4. Then there are only how many other cards? 48 other cards. So out of 48 other cards, we're choosing only 1 because it's a 5-card hand. Now, what is the total amount of hands we could have? Out of 52 cards, we're choosing 5. So that's the total hands. That's our total. And that will give you your answer for that one if you plug that into your calculator. Now let's look at the next one. It says 4 10s and an ace. So how many 10s are there in a deck of cards? There are 4 10s. How many are we looking at? Well, we want all 4 of them in our hand. And we also want an ace. So out of 4 aces, we only want 1. Now, once again, we're choosing out of 52 a 5-card hand. Those are all possible 5-card hands. It's out of the total 52 cards. Now the next one's looking at it. It says we want a 10, jack, queen, king, and an ace. Okay, so there are 4 10s, right? But we only want 1 out of those 4. Just like there are 4 jacks. But we only want 1. There are also 4 queens. But we only want 1, 4 kings, and we only want 1, And there are 4 aces, and we only want 1. I'm just going to put this so we could organize them a little bit better. Now all of this is over. Well, there are 52 cards in the deck, and we want a 5-card hand. This can be simplified. I'm just going to put it over here so I don't run out of room. As 4 choose 1, multiple all over 52, 5, 52 combination 5, and this is all to the power of 5. We can look at it that way, all to the power of 5, because if we look at it, 4 choose 1, multiplied by 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 4 choose 1. No use going into your calc and going to the math that many times. Just go 4 choose 1, put it in brackets, and go to the power of 5. Or push enter to the power of 5, then we divide that by 52, choose 5. A lot faster, a lot easier, kind of a nice little shortcut. Now let's take a look at this next one, D. We're saying at least 1 jack. Well, this goes back to a couple lessons ago. Remember we did probability when it says at least 1? That's a lot that we could choose. We could have 4 jacks, we could have 3 jacks, we could have 2 jacks, or we could have 1 jack. But what can't we have? We cannot have 0 jacks. Makes it easier. So we do not want 0 jacks. So the probability of picking a 5-card hand is 100% of everything. And we're going to subtract the 1 we cannot have, which is the probability of no jacks. Okay? So probability of no jacks is the only thing we don't want. What is that equal to? 1 minus, well, probability of no jacks is, you look at that, that's going to be, so out of 48 cards, because we're not including jacks, there's 48 other cards besides jacks, we are choosing 5, divided by, out of 52, choose 5. So that's the probability of getting no jacks, because we're only looking at 48 cards that we want. And we calculate that, and that will give us our answer. That's kind of a shortcut for it. Alright, so, next one says, the word counted has been spelled using Scrabble tiles. 2 tiles are randomly chosen, 1 at a time, and placed in the order of which they were chosen. Determine the probability that the first tiles are C and O. Now here's an interesting thing. The first one, we're looking at deck of cards. Now whenever you're playing, order doesn't matter, because remember, when you get cards, you rearrange them in your hand, so order does not matter. This next one here, it says, placed in the order which they were chosen. So we want to know if the first 2 letters, so there are 7 altogether here, were C and O. Well, if I take a look at that, C and O, there's only one way it could happen, C and then O. Order matters. And that's all over. Out of 7, we want the first 2, choosing, or 7, not choose, sorry, not combination, it's pick 2, because order matters, right? Okay, because in this case, order matters. So 7, permutation 2. And we put that into our calculator, and that'll give us our answer, because there's only one outcome we want, which is C and O, C and then O. And altogether, we have 7 letters here, and it's out of 7, pick 2, which the order, we only want 2. Whatever the order those 2 came in, that matters. So the next one says both are vowels. Well, there are 2 ways of doing this. We want 2 letters, right? 1, 2. Well, what's the probability of getting them? Well, both are vowels, so that's 1, 2, 3. So there's 3 for the first one, and then 2 for the second. Once it's used, there's only 2. That's fundamental counting principle, going that way. Now, the bottom, how many do we have altogether? We have 7 for that one, and we have then only 6 for the next one. So we could do this way, which is a nice little short way, or we could use permutations. Well, we have, out of 3 vowels, we're only wanting vowels, and out of 3, we're picking 2. Permutation 2. Out of 7, permutation 2. This is the other way we could do it. Okay? So those are the 2 ways we could do it, and they'll give you the same answer to try and calculate it. Because order matters, and picking vowels. So there's a total of 3 vowels, 1, 2, 3, and we want 2. And there's 7 others, we count those up, and we want 2. Okay? That's our total amount of permutations we could have. This is permutations wanted. And that's probability. It's always wanted over total. All right. Now, let's take a look at this. Example 4. So, example 4 says, Mike MP3 player contains 50 songs. If he listens to 10 songs at random, determine the probability as a percentage to the nearest hundredth that the playlist contains Mike's 2 favorite songs. So, we're looking at this. Does order matter in this first one? It just wants his 2 favorite songs. It's on random, so it's 10 songs on random. This is my key thing here. Random. So, it wants his 2 favorite songs. So we look at that. Those 2 songs must be chosen, right? 2 choose 2. Now, how many other songs are there? Well, out of 50 songs, he has 48 songs. And it's a list of 10, so there's 8 other songs out of those 48 that he is choosing. Okay, that he is going to have. So it's a combination. So it's 2 combination 2 multiplied by 48 combination 8. That's the wanted. Now all total possibilities is out of 50 songs, he has a combination of 10. So when we calculate that together, I'll just quickly do that on the calculator here. I'm going to get, clear that off, and we try that out. So it's 2 math, choose 2, which is 1, multiplied by 48, choose 8. So that's that, and we're going to divide that all by 50, choose 10. Which gives me 0.367. So nearest hundredth, 0.37. 0.037. Okay? So that is, you might say, 4% chance. So he has a 4% chance of that happening. That both of his 2 favorite songs are on there. Now let's look at B. One of his 2 favorite songs at the beginning of the 10 songs, and the other at the end. So now if we're looking at this, it says one's at the beginning, other at the end. That means order matters. So, because we have a beginning and an end, and we're looking at that, it's very important. Order matters. So once we hear order matters, what must we use? Permutations, or fundamental counting principle. I'm going to first start off with fundamental counting principle. If we look at the fundamental counting principle, I have 2. There's my first one, my last one, 1. Because it's his favorite and his other favorite song. And in between, we have 8 others. Those are the 8 others in between. Now, this is going to take a long time to do, because I have to go, well, there are 48 other songs. Then once that's chosen, there are only 47. Then when that's chosen, there's only 46, and it goes on and on and on. Now, what is that all out of? Well, here, this is 50 multiplied by, and then we have 49, because there's 49, 50 that could have gone in there, 49 in there. Then we have 48 in here, and it keeps on going on and on until we're done. So that's a long way of doing it. We could do it that way, but there's a faster way, and that's why permutations are so nice. So we could go this way. So when we start this off, we could have, out of 2, what does he want for the order? It's 2 favorite songs, 1 at the beginning, 1 at the end. That's 2 permutation 2. Now, in between, out of 48, he is choosing, or he wants, he's picky about it because order matters, another 8s in the middle, right? Then all of that is going to be out of 50 permutation 10, because that's the total amount of orders he can have, out of 50 permutation 10. Okay? So what does that give us? We have to put this in our calculator. So once again, take our trusty calculator, we go to math, permutation, to enter, which gives us 2 multiplied by, and it's 48, math, permutation 2, enter. And then we have to divide that all by, oops, I made a mistake. It's 48 math, and we have to go permutation 8. And then we're going to multiply that by 2, divide by 50, put my brackets there just in case, 50, permutation 10, which gives me, really small probability of that. That is 8 times 8.1, I'm just going to say 8.2 times 10 to the negative 4, okay? In other words, that is 0.0008, I believe. 1, 2, 3, 4. Yep. 816. That is the whole thing. Okay? So percentage to the nearest hundredth. Oh, I did that one, but it was 4 point something. 4 point. So this one here is 8. This one, percentage to the nearest hundredth, it is 0.8%. 0.08%. Okay? Okay? There we go. Now, last question. We're looking at the city council. So city council consists of 9 men and 6 women. 3 representatives are chosen at random from an environmental subcommittee. So what is the probability that Mayor Jim Milanovic and 2 women are chosen? So this is an interesting thing. Mayor Jim Milanovic is 1 person, so it's 1 out of 1. So this one right here, if you're making a council, order doesn't matter. As long as you're chosen, you're on, it's good. There's no hierarchy. So out of 1, we want Mayor Jim Milanovic. So that's, he's actually a boy, but we're only looking, he is 1 person. It's specifically him, not just any boy. And then, out of the 6 girls, we want 2 of them. Now, altogether, out of 15, there are 3 people wanted. So when we do that, we end up getting 3 out of 91. Okay? Now let's look at B. What is the probability that 2 women are chosen if the mayor must be on the council? Well, the mayor must be on the council, so it's just there. So out of 6, we're choosing 2 again. So it's pretty much he's on there, and now we're looking only at 2 females, so we don't want any males. But now, out of all the people that could be selected, the 2 other people that could be selected, the mayor isn't one of them. So instead of having 15 people, 9 and 6, we really only have 14 to choose from. And this gives me 15 out of 91. Okay? And that gives you a certain percentage for the probability. Now, last question. A hacker is attempting to break into a friend's security protected file. The friend tells the hacker the numbers that are in the 4-digit PIN, but not in the order of or how many times each digit may be repeated. So his friend's pretty happy. He's like, oh, you think you're a good hacker? Let's see if you can figure it out. Now, determine the probability that the hacker correctly guesses the 4-digit PIN on the first attempt. And if his friend tells him the PIN contains, so the first one is 4, 5, and 6, and 7. 4, 5, 6, and 7. So we have 4 letters, right? So it must contain those. So basically, that is the same as 4. We could have 4 for the first one, and then 3, then 2, and then 1. Different options for each digit. That's just 4 factorial, right? Well, 4 factorial is the same as 24. Now, there are 24 different combinations of these 4 letters. That's what we're looking at, 24 different combinations. Now, only one of those is right. So our answer is 1 out of 24. Okay? Now, the next one says only the numbers 4, 5, and 6. So we only have 3 numbers, but it's a 4-digit code. So that means one of those numbers is repeated. Well, which one is it? It could be 4, 4, 5, 6. It could be, it could contain 2 4s. It could contain 2 5s, a 4 and 2 5s. It could contain a 4, a 5, and 2 6s. So it could be any of these. But this isn't the exact order it could be in, is it? So really, still we have 4 digits, so that's 4 factorial divided by, well, my repeated, which is 2 factorial. Or we could have this with 2 5s, which is 4 factorial divided by 2 factorial. Or we could have 2 6s, which is 4 factorial divided by 2 factorial. Now, every time I say or, what does that mean? And means multiply. Or means to add. So we add all these numbers together. Each of these numbers, well, 4 factorial is 24, and so then 4 factorial divided by 2 factorial is going to be 12. So each of these is equal to 12. Now we have to add these all up, which gives me 36 different combinations. If he just tells you those are the ones. So if ones repeat, there's 36. So altogether, it is 1 in 36 chance that he gets it right if he just guessed. Now the last one says only the numbers 4 and 5 are used. So we're looking only the numbers 4 and 5. So first of all, we could have 3 4s and a 5. That's 1. We could have 2 4s and 2 5s. Or we could have 1 4 and 3 5s to make up the code. Now, I look at this and we say, well, this is the same as 4 factorial divided by 3 factorial, because we have 3 4s repeating. Next one is the same as saying 4 factorial divided by 2 factorial multiplied by 2 factorial, because we have 2 4s and we have 2 5s. And the last one is 4 factorial, because we have a total of 4 digits, divided by, well, 1 factorial for the 4, 3 factorial for the 5, because there's 3 repeated 5s. So what does that give me? Altogether, that will give me 14 different solutions. So we get 14 different solutions, which is the same as 1 out of 14. The probabilities, only one of those is correct. So now let's look at the last one. Only the number 4. So we only want the number 4. Well, that means everything is 4. That's it. Doesn't matter the order of those are in. No, that's everything. So he'll get it no matter what. He has a 100% chance of getting it. And that's it. So see you tomorrow while we work on our assignment together. Good luck.